Okay, I'm going to show you this because I think it's very interesting, but I'll start you off with a simple example. Newton's law of cooling basically says the following. It says that when a temperature is removed, when an object is removed from a warmer temperature to a cooler temperature, the temperature can be modeled by this function where T sub E here is the temperature of the environment, and the T naught is actually the initial temperature of the object, and K is your constant, and then little t represents the time T. So the temperature can be modeled by TE plus T naught minus TE times e to the KT. And so this is actually an exponential function because you have this e to the kt here. So you have an exponential function. So let me give you just a simple example. Suppose a canned soft drink takes 5 minutes to cool from 75 degrees to 65 degrees after being placed in a refrigerator that maintains a constant temperature of 35 degrees. Okay, so you have a can of soda that's at 75 degrees Fahrenheit, and after 5 minutes in this fridge it reduces the temperature to 65 degrees Fahrenheit. From that information we can actually get a model that models the cooling of this soft drink, and then we can answer these two questions. One says, what will the temperature of the drink be after 30 minutes, and then when will its temperature be 38 degrees. So basically, let's look at what we know here. The initial temperature of the soft drink was 75 degrees. The temperature of the environment in the fridge is 35 degrees. And so the initial temperature, which is the 75 degrees, minus the temperature of the environment, 35 degrees, is 40 degrees. And we know that T reduces to 65 degrees in 5 minutes. So if we put all this information into the formula, we can get K, our constant, rate of growth constant, or actually rate of cooling constant in this example. So using this formula, I'll put in the temperature of 65 degrees, and I'll put the time in here to be 5 minutes. Now you can do this in any units of time you want as long as you're consistent. Alright, so 5 minutes. So I'm going to put the 5 here and the K to the right. Now we know that the environment is 35 degrees, and we know that this difference is 40 degrees. So now all I have to do is subtract this 35 from both sides so that it'll cancel here, and then when I subtract 35 from 65 I'll get 30. So I'll get 30 equals 40 e to the 5k. And then if I divide both sides by 40, so just divide by 40 here, and then of course divide by 40 here, and 30 divided by 40 is actually 0.75, so I'll get 0.75 equals e to the 5k. And then to get k, I can take the natural log of both sides, so I have the natural log of 0.75 is equal to the natural log of e to the 5k, and we know the natural log of e to the 5k is just 5k. So I have natural log of 0.75 is equal to 5k, and then just divide both sides by 5 to get the k value. And when I put this in a calculator, I got negative 0.05754. So now I can take this number now and I can put it back in here. And let me go ahead and give you the model. Here I just answered the question, but let me give you the model, the new model. So the model for this cooling would be 35 plus 40 times e to the negative 0.05754 times t. Now to find the temperature after 30 minutes, now it didn't say additional 30 minutes, it just says 30 minutes. So if it said additional 30 minutes, I'd put 35 in. But it says after 30 minutes, so that means 30 minutes from the time we started. So we put 30 in here. And then we get 35 plus 40 times e to the negative 0.05754 times 30. And one thing I'll caution you to do when you put it in a calculator is put this exponent in a set of parentheses. And so I ended up getting 35 plus about 7.1. So it's cooled down to 42.1 degrees. Now the second question says, when will its temperature be 38 degrees? So I just need to put a temperature of 38 degrees here, and then I can solve for the T once I put that in. So let's put 38 in here, and then over here you can barely see the T, but there's a T right there. So now subtract 35 from both sides and I get 3. Then divide both sides by 40, and not sure why I wrote that twice, but anyway, divide both sides by 40. So 3 divided by 40 is 0.075. So I end up with 0.075 equals e to the negative 0.05754 t. And then take the log of both sides. So take the natural log of each side. And then, as you know over here, when you take the natural log of this, you just get the exponent, negative 0.05754 t equals to this natural log. And then to solve for t, just divide both sides by the negative 0.05754. And when I did that, I got 45 minutes. So in 45 minutes, it should reduce the temperature down to 38. The temperature down to, what was the oh yeah, 38 degrees. So it should take it 45 minutes to reduce the temperature to 38 degrees. And that's how Newton's law of cooling works. Now what's interesting is Newton's law of cooling is used for pathologists to determine the time of death. So let me just kind of give you an example of how this works. I know this might sound a little morbid, but if you want to be a scientist, it's very interesting. Suppose a body is found in a room, and the room has a constant temperature of 72 degrees Fahrenheit. The temperature of the body is taken and found to be 85 degrees. 30 minutes later, the temperature is taken again and found to be 81 degrees. Estimate the time of death. Okay, well, we can let T0 be 85. That's the body temperature when we first measured. And then the temperature of the room is 72 degrees. So if we take T0 minus TE, we get 13. The difference is 13 degrees. So using this formula, we put the room environment's temperature 72. We put the difference of these numbers here, 13, e to the kt. Now, we know that we can use t equal 30 minutes. The time is 30 minutes, and that gives us a temperature of 81. So I'm going to put a temperature here. I'm going to replace the temperature with 81 degrees, and I'm going to replace the time with 30 for 30 minutes. So now subtract 72 from both sides, and I'll get 9 equals 13 e to the 30k. Then divide both sides by 9/13, and I just left it in fraction form this time. So divide both sides by 13, I get 9/13 equals e to the 30k. And then you can take the natural log of both sides here, so you get the natural log of 9/13 equals the natural log of e to the 30k. And then the natural log of e to the 30k, remember, is just 30k. So I'm going to put it on this side. So we get 30k equals this natural log. And then to solve for k, just divide both sides by 30. So actually that 30 shouldn't be there. Okay, so divide both sides by 30. So if you divide this by 30, you just get k. And then if you divide this by 30, you get natural log of 9/13 divided by 30. So now we get negative 0.01226. And that's my constant. That's my constant for the cooling constant. Okay, now let's put k back into the function. So if we put k back in the function, remember our function was 72 plus 13 e to the negative kt. Well, now that we know k, we can put k in, and we get 72 plus 13 e to the negative 0.01226 t. Now, the trick here to find the time of death is to remember what is the body temperature normally. Your normal body temperature, obviously when you're alive, is 98.6 degrees. So I'm going to put 98.6 degrees in here, and then I'm going to solve for this value of time, and that'll give me the time when the temperature of the body was 98.6 degrees. In other words, the time when the person was still alive. So let's see what I'm going to do. I'm going to subtract 72 from both sides again. So 98.6 minus 72 gives me 26.6. So I have 26.6 equals 13 times e to the negative 0.01226 t. And then divide both sides by 13. So I didn't show that, but that's all you're going to do. Just divide 26.6 by 13. And when I did that, I got just a hair more than 2. I got like 2.0462. So I get 2.0462 equals e to this power. And then if you take the natural log of both sides, you get the natural log of 2.0462 equals the natural log of this. And then, of course, we know the natural log of e to a power is just the power. So I get, on the right-hand side, I get negative 0.01226t. And then if you divide this into this natural log, that'll give you t. Now notice I get a negative value, negative 58.4 minutes. Okay, well that makes sense because the time of death should have occurred before we took our initial temperature. Remember, in this example, t equals 0 is when we took our initial temperature, so the time of death occurred approximately 58 minutes before we took that initial temperature. So then all we would have to do is just go back from the time that we took the initial temperature, about 58 minutes, and that would give us the time of death. And this, of course, is in practice is not exact, obviously, but you know, it does give a pretty accurate window for the time of death in most cases. And in practice, this information is entered into a computer program, but obviously somebody had to work with this cooling function in order to enter it into the program and to program the computer program to work correctly. All right, well that pretty much ends this section on exponential and log applications, and actually it ends the module for this course for that first module over algebra and functions.